Welcome back. During the course of this video, we are going to perform a statistical analysis and as well visualization of our results using Limma and ggplot2. Historically, Limma has been mainly used for microarray and in the couple of years has been used for RNA-seq and very recently for proteomics analysis. Limma stands for linear models for microarray analysis, and as I mentioned, it has been very used. More than 6,000 citations has been published using this package. So it's a very important tool in bioinformatics, historically speaking. Limma, as well, for RNA-seq has another package that is called VUM. We are not going to discuss it for this course, but it's another tool that if you're very interested in RNA-seq analysis, VUM is an implementation of Limma for RNA-seq data. In the recent years, it has been developed implementations for proteomics data, which is the one that we're going to use in this course. So this, as you can see, is a very more nuanced code as we have been shown in the previous course. This is what we want to create if we have a package in bioconductor, or if we want to give a book or a manual or a documentation or a hands-on for practice or for learning. So this will be the format for your hands-on searching as well. It will be a PDF file in where you are going to see code, explanation, code, explanation. So in here, these chunks are the explanatory paragraphs for each step. And in the chunks, as they call it, are the codes. So without further ado, let's start to run the Limma analysis. So the first thing and most important thing to do is to set your working directory. When you download or you are going to analyze some data, you need to first be very specific in where you put it so you know where you're going to perform the analysis. So I already given the working directory, and I am just going to run the whole line as well as previously and run the selected line, and it will give where I am located. If I want to know where I am, I type get working directory and I go and I have my current working directory in the console. Since we already know how to activate Limma and ggplot packages, we are just going to highlight two lines. This has not been shown before. This is the first time, so you can highlight as many lines as you want, but as long as you know what those lines meant. We run them and we already have the two packages already activated. Another way to see if you have packages that are activated in your session, you can see the checkboxes. Limma is activated and ggplot2, some other as well as graphics, as devices, and so on. So that's another way to double check if you perform the library function successfully. So after we set our working directory, we load our packages. You see a pattern up to this point. First we load the packages, first we set our environment, and then we set our dataset. So those are the three main lines and core components before doing anything else in R, specifically in every analysis, but specifically for R. So this line over here is the dataset. Usually R works very well with CSV. Tab delimited, space delimited files is a very well nuanced program for tables, specifically matrices or tables. Another word, it will be data frames as well, which is a more nuanced one. So this function is saying, well, if I have a CSV read CSV will be the function to retrieve a CSV file in this working directory. So my file, it has to be in this working directory. Another way to check if I have that file there is to go to Files, and as you can see, I have the demonstration dataset.csv. And if it's CSV, we need to specify that it's separated by comma. CSV stands for comma separated values. And we just load the line and we can see it here. So as I described in the RStudio videos, at your right in the environment you are going to see variables, functions, list, every data object, it will be in this section, and as well it will display in the console the last commands you run. We have different options to view the dataset. We can click it in here, or we can start just poking around on how to get the glimpse of what data we have. So head is for just get the first 5 to 10 lines of your dataset. You can be specific as well, but head is very well for small portions of the dataset. As you can see, I just select head and run it, and this is the display of the dataset that we are going to use. So already we can get a glimpse of how many replicates we have, what IDs we have in the dataset, and the values. This is very important. Proteomics, microarrays, and RNA-seq, what the difference they have is in terms of the numeric value, what those numbers represent. But in terms of analysis, we can abstract, we can go a little bit of an upper level and just say these are numbers, and we are just going to compare different replicates to get an important result in terms of statistical value. So in this way, we have 5 controls and 5 replicates. We have in the first column the protein accessions. Those are already given to us from the Proteome Discoverer. This data set, it has not been normalized nor scaled. These are directly processed through quantitation and Proteome Discoverer analysis, and they were identified with a given protein accession and description. We can see as well, in here we don't have a knowledge of how many proteins we have in the dataset. So a way to see if we have how many we have is to check in here. In here we are seeing that we have 1,884 proteins in rows and 11 observations, 11 variables. So each column represents a variable in the table. Another way to see it is to use the function dim, which stands for dimension. And you just want to see the same description as in here, you will see it in here. So you have a table of 1,884 with 11 columns or 11 variables. Another way to see displays of this dataset will be just to click in data, this table, and it will give the same information as we have been printing since the beginning, but in here we can scroll it and we can see as many as we want. Another way to activate and visualize this table is to use the function view, which is the same that if I click this in here, it will display in here. So if I run this line, it will print the same code and it will give me the same table. So after we have been observing the data and the columns that we're going to analyze, since Limma works in matrices, we are going to assign the accessions, the protein accessions of this table, we are going to give it as row names, and we are going just to get remaining with 10 columns. And a way to do this is to say in E, I want to eliminate the first column, and I want it as my row names. So all these values that I have in here will be substituted by my protein accessions. And this is very important because you will see in the future how we are going to use it and how we are going to do the analysis. But it's very important from the beginning what columns you need to analyze. Since first, the data that we have in protein accessions is not entirely numeric, it doesn't represent a replicate. It will just truncate the analysis even before we do it. So a way to know which protein is in the matrix or in the table is, instead of deleting it, we just give it as row name, and then we save a very long time into process later on. So we just run this command, and as it is, it's run. It will overwrite if I don't give another variable name. So it will overwrite the table that I have already presented to you. So as we have been discussing, now the protein accessions are your row names, and now you end up having only 10 columns at display. And now, since this is a table, a CSV, and Limma works in matrices, we now need to convert the data frame to a matrix. So a way to do it is using the function. Now I want this as matrix of E, of this data frame, of this table that we have been analyzing. And then we run it. And now you see the difference. Now it's not entirely a data frame where actually is the same information, but now is a matrix. But in the way that it's represented is not as a data frame, not as a conventional table, is now a matrices. And just to confirm as well, again, we can run dimension. And now instead of having 11 as previously, we have now 10 columns with the same number of proteins. So you don't lose data. You are just changing and transforming your data set in order to do your analysis. And since this data is in protein abundance, this is a very critical step. This is one of the most important steps to run any Limma analysis at all. It doesn't matter if it's RNA-seq, microarrays, or proteomics data, specifically TNT in this case. So these values are here, represents protein abundance that were processed using the proteome discovery. So in order to analyze correctly in Limma these replicates, we need to transform the data into a logarithmic distribution. So a way to do it is to insert the matrix as well as the variable and call for logarithmic, this function logarithmic, and insert your matrix as the one you want to transform. And this number stands for the base of the logarithm. Usually, since the microarrays analysis, the most common logarithmic scale is base 2. So this number stands for logarithmic base 2. So you're saying, I want to convert this matrix as a logarithm base 2. And we are going to run it. And now you see something that now I have a different values, different scale as well. So if we just click view, which is the same command, now you see that the values of all your replicates across all your proteins are in log2 base. And this is very important. And after we have our data transformed, we need to normalize it. There are several normalization methods, but the most one of the most used is the median polish, median normalization. So this normalized data, so each row per column will have the same median value, so it can be comparable between groups per protein. So a way to do it is to use this function provided by Limma, which says normalize between arrays to your matrix, and the method we want, scale. Scale stands for another nomenclature to call median normalization. And we are going to perform the normalization. It's already done. And we can click view. And you see that the data has been normalized. So after the data is normalized and logged to transform, we are almost ready to perform the Limma analysis. But first we need the hypothesis testing. We need the scientific design of what comparison we want to make. So we are ready in this data set. We have given already the columns and what columns are represented as controls and what columns represent as cases. If we take a look again to our matrix, we can see that in the columns they are already labeled as control from replicate 1 to replicate 5. In the same case for cases, case from replicate 1 to replicate 5. This will be very important because the way that Limma works is to give a design, is to give what column corresponds to what group. And that's why it's versatile in the kind of analysis you want to perform. In this scenario, we're going to just perform a two-group comparison. But there's another analysis that are even two groups in two different experiments, which is called 2 per 2 factorial. But since most of the scenarios in bioinformatics are between cases and controls, just a simple comparison, this is the most basic design. So each one represents a column. So you notice in here that I have 5 controls, 5 cases. So and those corresponds to the ones that I have in the matrix, those that comes from the matrix. So another way, so we are going to run more than one line because we are going to run the whole thing, or we just won't have to highlight the whole thing as well. We can highlight, or we can just run from the beginning or from the end of each variable, and it will run it as well. And we're going to run it, and now you see that we have these values. So a way that we can see what we have is to actually, we can just copy and paste this in the console. This will act as print. And we see that we have only 2 different labels. We have 5 controls and 5 cases. So now we have established what the comparison we have. And this is now the design of the matrix. This is where we are going to say, I want this comparison to be made. I want case versus controls. So this design will be the line that we are going to declare, that this will be the analysis that we want to perform. This will be essentially the introduction to our hypothesis testing. So as you see here, now we have something more developed, something more of what column, what column, what replicate corresponds to a control, what replicate corresponds to a case. And you see that wherever you see a 0 is because in the first 5 columns they are controls and in the last 5 they are cases. It's the same in here. So this is the design for Limma to say this column is case, this column is control. Control in the model will be the intercept, will be the variable to not observe change, and case will be the category to see. I want to see the difference between the controls using case as the one that has the change. In this line as well, we are going to give the names that we have already designed in here. So we just run it, and they already being labeled. So we go further, and this is where we are going to run our regression analysis, our linear models. So fit, LM fit will be our linear model analysis, our linear model fit. And here we are going to say, well, I want my matrix to be analyzed as our design, case versus control. So we fit the model, run it, and then the comparison will be in contrast matrix, and this will be the hypothesis test, the difference between cases versus controls. And here you say the logarithmic base 2 mean, because Limma what it takes is the group means of the log 2 abundances per cases versus the controls. Limma what it takes is the group mean of cases versus the group mean of controls, and that's how it will calculate the log 2 fold change. So we are going to run the contrast matrix, and as well the contrast fit. Something interesting here, the fit, it will show in here. So in here you can see the coefficients. You can see, if we select this tab over here, it will display fit coefficients, and we can print it out, and we can see the fitted coefficients for our analysis. Case and control, those are the group means that are being calculated. And of course it will give you the first 500, but the total of proteins are 1884. So something that is a plus to understand this. We, as you're seeing these values in the console, in here, we are running for each protein a linear model. So we are essentially running 1884 linear models in total. And each one will have be given a fold change and p-value and a correction of that p-value. Since Limma as well infers from Bayesian perspective, this function will use the contrast we already performed for the linear model into a Bayesian approach, which in turn will be performed for our moderated statistics to analyze how significant the fold change, the log2 fold change, is between the cases and controls. So we run our Bayesian analysis, and it has already the fit for Bayesian analysis. As you see already, the values are already calculated for the fold change. So those are very crude log2 fold change. Let me just clean the console. And now this is a very interesting function. This is where it will display the log to fold change statistics analysis that was performed, p-values, and the adjusted p-value. So in a nutshell, this function is saying, well, the e-base fit that I ran previously to get the statistics and as well to compare if the fold change was significant or not, I want to perform and I want to create a table that summarizes all these analysis that we have been doing in the linear model. So we insert this as the variable for top table, and adjust stands for the p-value adjustment or p-value correction that we want to perform. Usually, as was described in the lecture, the most common are Benjamini and Hochberg, Bonferroni, Home, and it will depend as well in the number of variables you are analyzing. So in this case, we are using Benjamini and Hochberg. And since we know already the number of observations, the number of models, the number of proteins that we are analyzing, we can give the whole list. But the default, it will give the top 10 results. It will give you the top 5 differentially abundant or upregulated, and it will give you the top 5 less differentially abundant or downregulated, as is described in microarrays and RNA-seq analysis. So we run it, and it will be a data frame, not a matrix in this case, and we can open these results. So in here, you see that in the whole analysis, in the whole pipeline that we have been running since the beginning, we have the row names still there for each protein. Now we have the log fold change, the T statistics results, the p-value, and the adjusted p-value as a Bonferroni correction, as well as the log odds of the analysis, which stands for the probability of if this gene was actually, in terms of logarithmic value, expressed in how significant it was. But the most impactful and the most important columns of these results are log fold change, p-value, and adjusted p-value. So this result already, we can sort it by expression. Let's say that I want to see the most upregulated proteins. So most of the time, the log fold change can be an arbitrary approach. So we can check in here that we can have a cutoff of some significance in a log fold change of 0.58, which stands of the same as a fold change of 1.5. And at least we have 4 proteins that are above or equal 1.5 for logarithmic fold change, and they are significant, but only from the 4 of them, 3 are true positive that are significant in this analysis. So another way to visualize this, since they are many of them, they are actually all of them 1884, we can visualize this. We can represent the results in a visualization. We can visualize this data. There are some plots to visualize expression or abundance results. One of the most common plots that we would like to show for these demonstration purposes is the volcano plot. Maybe some of you will be familiar with the concept, some of you won't, but essentially we are going to display a volcano plot which it represents the dispersion It's a scatter plot that it shows in terms of log fold change in function to the statistical significance, how many you can see that are above those thresholds, above the threshold that you set. Let's say in this example, we have proteins that are significant with a fold change of log to fold change of 0.58 and a p-value of 0.5. Let's say that those are values to represent the volcano plot. So in here we are just from this table we are just taking a subset of only the first column and the p-value. Those two columns will be the ones that we are going to use. So first we are going to create a new data frame. This is something new. This is something that it hasn't demonstrated before. So in this case, we are going to extract data to create a new table. So this only will have these two columns from here. Another way to see it, as in the previous lines, is with head. It will display the first 5, 6, or 10s. It depends on the ones that you wanna display. And this whole chunk of code is the volcano plot in Canvas. It's saying I want with these specifications the design of my volcano plot. So in a nutshell, this in here is saying, well, I want every protein that is with a p-value below 0.05 and a log fold change upper or equal to 0.58 to be considered as up, either down. If they are not significant by either fold change or p-value, label it as not significant. And this is the function that this is the function that requires to have ggplot installed. So it's literally ggplot the data, which is your table. The x-axis of the plot will be the fold change, and the y will be the log, the negative log base 10 of the p-value. So let's just highlight the whole code so we can demonstrate it. And as is shown, this is the result of the volcano plot. In here, we can actually, if we select zoom, it can display in a wider image external from R. As described before, in the x-axis you will have the log fold change, or in some cases you will have fold change as well. So you can represent either of it. In this case, it will be log to fold change and the negative value of the p-value in here. Every dot in here represents a protein in terms of fold change and p-value. Notice that our thresholds are met. We have 4 proteins that are significant in terms of p-value and fold change, and the rest, even though that they may have demonstrate a good fold change or a good p-value like this one, they are not significant in terms of the 2 parameters. So, and that's very important. We cannot report fold change without a p-value. And this here represents only those 4 proteins that were significant for p-value. We can as well check for the adjusted p-value, in which, as predicted, this protein in here, it will be highlighted gray, and only these proteins will be the ones that are considered significant. We can do that very quick. We are going to substitute. This is something new as well. If we want to substitute with one of one more instance, everything that represents the p-value, we can change it. As long as we know the column that we want is adjusted that p-value, p.val. Let's just check it a little bit. P-val, threshold, p-val, everything in uppercase. And we replace the 5 positions in where we had previously p-val. And now we want to see only the ones that are true positives with Benjaminian Hochberg correction. So we run the whole thing. It will override for us. We can clean the console, we can clean the plots, and now we are going to run this. And now, as you can see, we have the adjusted p-value, which are the ones that are in here, the same values. And now we would like to run it again, but now it will be with the adjusted p-value, not the raw p-value. So as predicted, let's just zoom it again. So now we have the new plot, but with only the adjusted p-value. And notice that now the protein that was considered previously as differential abundant now is not. Now with the Benjaminian Hochberg correction, we end up having only 3 proteins from the analysis. So after all this analysis has been done, another approach is to understand what these proteins are, what functions they show, in what pathways they are related. And for that, in our next demonstration, we are going to use ingenuity pathway analysis to do the enrichment analysis of these proteins. So thank you for listening. Thank you for your attention. And we're going to see in our next video using ingenuity pathway analysis.